we're going to kind of wrap up today the directing effects and substituents. And we'll look at multiple substituents and what kind of, how do you make a decision, where does the new substituent go to the third substituent, and it's actually pretty easy to make this prediction. And then we'll talk about a few other other reactions that have to do with aromatic rings. So these are kind of not electrophilic aromatic substitutions, but they're and they require really harsh conditions, but they allow some interesting reactivity for benzene. So we can categorize the substituents we've learned so far based on their ability to activate an EAS reaction. So they're either going to be activating the EAS reaction or deactivating it. What I mean to say is, like, activators, they make the EAS reaction go faster, and deactivators make it go slower. So there's either activating groups or deactivating groups. And then if we go into each of those categories, activators and deactivators, there are subcategories. So, for instance, in activators, we have things that are really strongly activating, and they have things that are not so strongly activating. So things in the middle and things that are pretty weak. Okay, so you got weak activators, strong activators, and something in the middle. And the same is true for deactivators. They're strong, I should say, deactivating. Sorry. There are things that are really, really good deactivators and things that are not so good deactivators. And that's an important thing to know, because that will change the way multiple substituents interact on the ring. And it's actually just a matter of really looking at the molecule structure, the substituent structure, and making a decision. So let's look at these first, this row here. We have lone pair electrons on the atom directly connected to the aromatic ring. And so are these, like, we saw some already, like anisole, right? Anisole is like this. Let's redraw anisole. Was anisole strongly activating or kind of weakly activating, from what you remember?
Pretty strong, right? It was like 400 times.
It was like 400 times more activated than just benzene alone. And we attributed to that to the fact that it has lone pair electrons that can donate into the ring. And those are directly adjacent to the aromatic ring. And so all of these examples have the same situation, right? We have lone pair electrons that we can delocalize into the ring, so we call them electron donors. Would it be fair to say that these are probably strongly activating them? Yeah, and we would assume so, and it turns out to be true. All of these examples activate the ring very strongly. These are the strongest of all activators because of that lone pair electrons. So we'll say these are strongly activating. So when you see a pair of lone pairs directly attached to an atom like that, you want to think of it that way, right? You want to make that assessment as probably a strong activating group. That would be a fair prediction. Now let's look at this next set. What's different about this set? I don't know why anisole is there, but what's different about this set compared to the top row?
It has resonance by itself.
There's some resonance that it can participate in not having to do with the ring, right? So we can think of resonance forms like donating into the ring, right? But we could also think of them going out of the ring like this. And really what that's saying is that it attached to each of these electron donors, these are electron donors, these oxygen and nitrogen and so on, there's an electron withdrawing group attached to those, right? So in this case, there aren't any electron withdrawing groups really attached. I mean, hydrogen isn't really going to be very electron withdrawing. But in each of these, we have a carbonyl system attached to our electron donor, and these themselves are electron withdrawing groups. So what effect does that have? Are these going to be as strong activators? No, they should be weaker, and it turns out they are. So we'll categorize these as moderate activators. They still have that lone pair to donate, but they're not nearly as good as our phenol and anisole. So these are moderate. All right. And now we have alkyl group substituents, like a methyl group, an ethyl group, a isopropyl group, and a terbial group. And so do we expect these to be activating or deactivating based on the things we've seen so far? These are also activating, like toluene, right? So we have a methyl substituent here that's toluene. Now it's activated. But anisole, remember, was way more activated than this. So what's making these not such as strong activators?
Because they don't have a lone pair.
They don't have a lone pair to donate. What makes them activators at all, though?
Is it hyperconjugation?
Yeah, so these participate in hyperconjugation. So remember in our EAS, we can generate a carbocation, like here, for instance. And hyperconjugation stabilizes that. That's what all these alkyl substituents are doing. So these are activators based on hyperconjugation. But these are not nearly as strong as our lone pair donors. So we'll call these weak activators. Okay, now we're down here at one of the exceptions to this rule, the halogens. So this is when we have a fluorine or bromine or an iodine, but we left fluoride off. So these have lone pairs helping them to donate, right? But they're also deactivating because of bond polarization. So these would be also, we'll call these weak activators. These are weak activators that also happen to be meta-directors, right? Okay. Okay, so now let's look at some other examples. What are we in now? Are these activators or deactivators? Yeah, these are all electron withdrawing groups. So these are deactivators because of resonance. And they all have a carbonyl adjacent to that. You'll notice that there's always some carbonyl or a pi bond that electrons can delocalize into. So that's why they're electron withdrawing. There's no lone pairs. It's exactly the opposite. And all of these are meta-directors. Oops. And they're deactivators because of that. And these are all, I would say, these are moderate deactivators. And now we're down here at the nitro group. We remember that. Why are these are strong deactivators. And I'm including in this group a positively charged nitrogen, like an ammonium ion, or an alkyl group that's fully substituted with halogen atoms. So why would like a nitro group, for instance, be more electron withdrawing or more deactivating than a carbonyl system, like a ketone or a carboxylic acid or an amide? Yeah, my nitrogen is more electronegative than carbon, so this is more electronegative. And then this is a special case, like CBr3, for instance. That's because we have a lot of electron withdrawing groups attached to a carbon atom that doesn't have any lone pairs. That creates a situation similar to nitrogen, where it's really electron withdrawn. So these are all strong deactivating groups. I think I made a mistake when I was talking earlier. Let me correct myself. On the halogens, I call these weak activators. These are weak deactivators. You can see halogens get really confusing because they're weak deactivators, but they have a lone pair. They're weak deactivators because of this bond polarization. And they're not meta-directors, though. They're OrthoPara directors. I apologize for that. Halogens are that funny exception. You just have to remember which exception they're accepting. So the way to remember it is the bond is polarized, which causes them to be deactivators. However, they have lone pairs on them that cause them to be OrthoPara directors. Okay? It's those lone pairs that cause the OrthoPara direction, and the bond polarization that causes the deactivation. Okay, so that's all cleared up. Multiple substituents. So when we're considering a reaction like this, where we have two substituents and they may have the same effect, or they may have different effects, right? One might be an OrthoPara director, one might be a meta-director. We have to think about all of those effects and try to take into consideration what's going to happen based on their relative positions. And it takes a little bit of just analysis, really, to think about it. You have to consider everything. And we're going to look right now at substituents that have, well, they're going to be competing for different positions. And we're going to look at how that works out, how that plays out in the end. So first off, you want to identify the reaction that's taking place. So what are we doing here with Br?
Adding a bromine.
We're going to add a bromine somewhere in the region. And then we want to look at our substituents and decide, okay, what are they? Are they OrthoPara directors or are they meta-directors? So we have a methyl group. Is that going to be OrthoPara or is that going to be a meta? So alkyl groups. These are weak activators. And they are OrthoPara directors, right? So what I like to do when I see an OrthoPara director like that is I look on the ring and I make a little dot to where it's pointing its effect. It's pointing in effect to the para position, which is already occupied, and to the ortho positions, which are here. So those are the positions the methyl group is directing. And then we're going to look at the nitro group, right? The nitro group, that's nitro, that's an electron withdrawing group, and it's a strong deactivator. It's a strong deactivator. And it's also a meta-director. So where it's pointing to is not OrthoPara, but the meta positions, which are here. So the only place really where this bromine can go, logically, is ortho to the methyl group, right? Or meta to the nitro, which is the same thing. So our product, we would predict the major product would be Is there any difference between this and that? No. There's flipomers, right? So we could take one and just flip it upside down, and it would be identical, right? Because the benzene ring is flat. So those are equivalent, and they're identical molecules actually. So there's no difference between them. So these are equal structures. Okay, so make sense? Okay, let's do another example. So here we have nitric acid and sulfuric acid. So this is a nitration reaction. And we have a hydroxyl, and we have a methyl. So the hydroxyl group, that's a strong activator. And the methyl group is a weak activator. Okay. So the strong activator is going to dominate. Whenever we have a strong substituent, it's going to dominate the effect that it's an activator. If you had a competition between a strong activator and a strong deactivator, which one do you think would win? Right? It's kind of an interesting question to think about. Anyway, let's get back to this one. We have a strong activator and a weak activator. And both are OrthoPara directors. So I'll use the symbol dot for the weak activator, and I'll put a little square around what the strong activator is pointing to. The strong activator is pointing towards the ortho and para positions, and the weak activator is pointing towards the ortho and para positions. So we have to decide, is the major product going to be and what do we think? A or B? A. And what's your rationale for that?
Because the strong activator is going to be the major product.
Right. Because a strong activator, what that's doing is causing the ring to be especially reactive at whatever positions it's activating. It's putting electron density there, whereas the weak activators not really doing that much work. They're just kind of lazy and sitting around, letting the other groups decide things. So I would say definitely A, this would be the major, and this would be the minor. But again, I mean, you'll see both. Both will get formed. Just like, which would you predict to be the major one? Okay, so let's do this. Now we have one where we have two OrthoPara directors, and they're OrthoPara to each other. And we have to consider also steric effects when we do this. So just looking at these two products, we can see, okay, they're OrthoPara directors. So, you know, we're thinking it's going to go here. why is there a meta product being drawn?
Because they're both OrthoPara.
They're both OrthoPara. Yeah, they're blocking para positions for each other, maybe?
Well, so because both of them are going to be directing in some effect, correct?
Oh, yeah, because the meta position is, sorry, ortho to the, sorry. Yeah. So we've got this meta, so this is ortho for the methyl group, right? So, right there. And then ortho for isopropyl here. So which one do you think would be the major product, A or B?
Okay.
Okay. And you're thinking sterics is the reason for that?
Mm-hmm.
Yeah, so exactly. So sterics, what do you think would be, no, that's not what So you can see now there's obviously an issue if you want to get something ortho to a sterically inverted group, right? That can be a difficult thing to accomplish. Even if the DAC is stacked to put it that way, right? It can be quite difficult to do. So that's a problem we're going to run into, and we're going to figure out how to solve it. So take a look at this one and try to predict major, minor. I basically just picked the one farthest away from the most sterically demanding group because they're both OrthoPara Directors. And the one that's never observed is shown here because it's ortho to both, which would be really unlikely to do. But what if you wanted to make that? You know, that would be a thing. That might be a challenge problem, you know, try to make this. So you want to think about how you might do something like that. And that example is shown here. What if you wanted to accomplish the ortho-bromination of a terp-butyl benzene? Like, you know, this is like, this take the problem to the extreme almost. So how do we do this? Well, there's a little strategy we can use that's kind of like protecting groups. What if we started with our terp-butyl benzene and we could temporarily, where's this terp-butyl benzene going to direct? Ortho, which is where we want, but everything's going to go to the para position, right? Okay, so let's use that to our advantage, because what if it puts something on the para position? Because then we'll block it, right? If we attach something to the para position, sort of like, hey, now nothing can go in the para position, so we'll put some kind of blocking group. Some temporarily indole blocking group, and then we do a bromination. Right? And the most important thing about this blocking group is that we can remove it so that we can get the product that we're interested in. So remove, block. And it should be really easy to remove and give us a high yield and not require a lot of extensive purification processes, so that it's something that we can do on an industrial scale without much trouble. Anyone have any ideas what we can use for that blocking group? So the reagents that we can actually use, show here on this slide. Remember this little reaction where we can put on a sulfite group, SO3H. We can also take it off really easily by using dilute sulfuric acid. So we can put it on and then take it off really easily. So this is the idea. You use fuming H2SO4 to put it on. It goes OrthoPara. And it's a meta-director. So it directs everything to where, and this is an OrthoPara director, so everything goes where it wants to, and then you just remove the blocking group. So that's the whole point of doing sulfonations, is so that you can make a blocking group. So it's reversible and convenient. So I'm just going to, now we're basically done talking about the EAS reactions. You want to read this section in the book on synthetic strategies and practice doing these problems. Practice, so that you get down the reactions. You want the reactions down cold, and how to get from like point A to point Z, without too much stress. So there are some, this is an important table in 19.2. This is a really important thing when you're doing synthesis of aromatic rings. A para director to a meta during the course of the synthesis, right? Because you install it as a meta director, but oh no, I need it to be an orthopara director. So for instance, a nitro group is a great example of that. We need to get a nitrogen there, but we want an orthopara director so we can reduce it to the amine. Another example of switching this is oxidation of the side chains. So you have a carbon on the side chain, and you oxidize it to a carboxylic acid, it becomes a meta director. Another example of that is this, where we take N-bromo-6-inamide. That's actually going to replace all the hydrogen atoms with a bromine and make CDR3, which is also a meta director and deactivates. And then finally, we can go the other direction from a meta to an orthopara director, doing a reduction. These are the clemency conditions for reducing a ketone. So those are just ways of switching directing effects. So you want to have those in your toolbox ready at your disposal. And also just remember some limitations. Here's one we haven't talked about. The limitation we have talked about so far is this. Remember that these are deactivators, and we can't do any Friedel-Crafts reactions once these are deactivated. Right? So we already know that limitation. These are sort of like the end of you want to do those last, right? The things that stop reactions, you want to do last, usually. Here's another limitation. Unfortunately, you can't nitrate an aniline derivative. The reason why is that when you expose the nitrogen of the amine to nitric acid, is it oxidizes to an N oxide. So this is a common problem with amines, actually, is they tend to oxidize over time, form N oxides. So anyway, you can't do this reaction. So if you wanted to accomplish this, you'd have to nitrate first. And if you want to have para, it would be tricky, actually, to do that. I don't feel like thinking about it right now, but there'd probably be a way to do this. Anyway, so don't try to oxidize your amine. Some things aren't really possible, actually, so don't worry, I won't give you one that's impossible to do. There's a couple of duplicate slides. Here's an example problem. If you want to try to work on this for a second, see how you might accomplish this from benzene. what's the problem that we have going on here? Where should I start? I need to, if I'm starting from benzene, I don't know any reactions that are going to go directly from benzene to this thing, right? There's no way. That's not yet. Actually, you'll learn some soon. Be like that. But not yet. So I need to go some other way. I have to attach carbon atoms. Is there any way to attach directly carboxylic acids to a benzene? No, no way of doing that. But we do know how to make carboxylic acids from carbon atoms that are attached to a benzene ring, right? So maybe we make something and we don't know what that is, but that's something we can turn into this. You do know a way to go directly from this to the dicarboxylic acid. That's CaMNO4 with under basic conditions, NaOH, heat. There are other conditions for that, but I just picked that one. So that's oxidation of side chains. So it's in it when we were doing the last chapter 18, kind of at the end of chapter 18. Okay. So then we just need to figure out how to put those two methyl groups onto the benzene ring. What's the problem with that? They're ortho to each other, right? We don't know any direct. This is an OrthoPara director, right? The methyl group. So if we try to make this, we'll also get a para substituted one. And then we'd have to separate it. But we want just where they're ortho to each other. So really, we have to make this one from this guy, right? And then deprotect it using dilute H2SO4 to deblock the sulfonate. Okay, and from this we know, probably not going to go directly there, we know how to put the methyl group on. What reaction attaches that methyl group in the ortho position? Okay, we've only learned two carbon-carbon bond forming reactions this unit. So we're going to use the Lewis acid catalyzed Friedel-Crafts reaction. So aluminum, we use aluminum trichloride. And we're doing an alkylation here. So we're not putting on an acyl group. So we can just use, and there's no rearrangement problems, right? Because it's just a carbon. So we can just use methyl chloride. And then we know how to put the sulfonate group on. This is fuming H2SO4. And we know how to do this because we just did that. We just use that. So pretty straightforward synthesis there. Whenever you see this, what two groups that are ortho to each other, you want to be thinking of blocking groups. Right? It's just a thing, and then you got to know your carbon-carbon bond forming reaction, which is Friedel-Crafts. That's how you're going to attach alkyl groups or acyl groups. That's your bread and butter. You got to know that reaction. If you don't have that tool in your toolbox, you're basically SOL. So you got to know that one. Any questions on doing that? I'll give you guys this one for homework to try. So work on this one. I'm going to design a synthesis of this from benzene. It's good practice for stuff. So practice these problems. You gotta practice multiple. They're pretty simple, but if you don't practice it, and this is the best way to learn the reagents is practicing the synthesis problems. So, okay, so now let's just wrap up this chapter with a few of these other reactions. So when you start heating things up a lot, you can get reactions that happen that you normally wouldn't see if you heat it up a lot and it doesn't burn. So here's an example of something that should look really strange to you. What is strange about this? Yeah, we can't do it's a substitution reaction, and it's not electrophilic. So there's sodium hydroxide here is not an electrophile. And we've been learning electrophilic aromatic substitutions. This is a nucleophile. And strangely enough, it looks like the OH has substituted for bromine. This is an sp2, right? sp2. And we know that there's no SN2 on sp2. So it can't be an SN2 reaction. It's impossible. We're not going to break that rule. We're not doing an SN2 reaction here. So it's got some other mechanism going on. And it requires a lot of heat. It has a leaving group, bromine, right? Bromine's a decent leaving group. We're going to try to figure out what's going on here. Here's a little interesting thing. If you do this, it doesn't work. So if you change it to a meta position, it no longer works. Only works when the nitro is para. This is why it's kind of a strange reaction. It doesn't have that much utility because it requires, if you want to get these reactions to work, what we're going to call nucleophilic aromatic substitution, you have to have a really strong electron withdrawing group para to an excellent leaving group. Otherwise, it just doesn't work. Okay. So the requirements for this reaction to happen, we have to have a very good or a strong electron withdrawing group that is para to an excellent leaving group. Okay, like bromine. Chlorine's not going to really work. You got to have bromine or hydrogen. Or there are some others. Sometimes you'll see examples where we have something called a diazonium. This is the best leaving group in the world. So it's N2, it leaves as nitrogen gas. So this can become an N2 molecule, which is really stable. You can use that as an inert atmosphere on a reaction. It doesn't react with anything. It's a gas. So when it leaves, it has a lot of entropy associated with it because it's a gas. So anyway, see these. This is called diazonium. That's when you have a nitrogen that's positive and there's two nitrogen atoms. So this is a requirement for a nucleophilic aromatic substitution. Really good electron withdrawing group para to an excellent leaving group. So this doesn't happen as a result because they're meta to each other. Okay. Let's go through the mechanism for this. What must be happening? So I want to redraw my molecule molecule because I want to show the nitro group when I'm doing this. So the hydroxide is going to act as a nucleophile, and it's actually going to attack that carbon, and then this bond's going to migrate down, and this bond's going to migrate down and do resonance out there. So it delocalizes the electrons. That gives us, for a second, this sort of tetrahedral intermediate. Where we have and you can see now why you need that electron withdrawing group, right? Because it allows those electrons to migrate down into it. And then now what happens, you can probably predict, it's like this reminds me of like a spring or something. Like you pull a spring and then you let go and it goes back. So these electrons are going to flow backwards, back into the ring to re-aromatize and kick off our leaving group to give. Right, it's kind of a cool mechanism. Really the only reason I teach it is because it's kind of a cool mechanism. Otherwise, it doesn't really have much synthetic use. Unless you want to make phenols, of course. It's kind of neat. So, now you know a way to make phenols. All right. Make sense? How that works? Okay. There's another one of these called elimination addition reactions, and this really requires extraordinary conditions. If you just take a regular benzyl chloride and treat it with sodium hydroxide, you get no reaction. But if you heat it up to 350 degrees Celsius, you can get a substitution between reactions to happen. Those are very harsh conditions, limited substrates. This is really good on industrial scales, though, for things like making phenol. Simple molecules that don't have a lot of other functional groups. You can get this to happen under mild conditions using really strong bases, it turns out. So instead of using really high heat, if you use something like an excellent base / nucleophile like amide, sodium amide, and liquid ammonia, you can get nitrogen to substitute. So this could actually be a way to set up our OrthoPara amine nitro group thing, actually. So it's kind of an interesting mechanism how this is happening. If you use toluene and do this, it's interesting. You get an ortho and a para and a meta substituted. So that doesn't really make any sense if you think about it for very long. It's not going through a nucleophilic aromatic substitution or an electrophilic aromatic substitution. And to figure this mechanism out, you can do an isotopic labeling study where you take one of the carbon atoms in the ring, the one attached to the chlorine, and you make it a C14 instead. You can do radioisotopic labeling. You can detect that using, there are a variety of spectroscopic methods where you can detect C14. And that's this carbon. And when you actually do that, you'll see that the substitution, the nitrogen, is happening on what we call the ipso, that's your direct connection carbon, and ortho to it. So what's actually happening in this mechanism is, I'll show it here. First, the amide deprotonates alpha to the ipso chlorine, so the alpha proton. And when it deprotonates it, it creates a resonance form where there's an alkyne in the benzene ring. That's why you need a really strong base to do this. You can imagine that's not the most stable thing in the world because these bonds are not 180 degrees apart from each other. So this is called benzyne. And actually, we're going to use benzyne later in something called we can use that in a Diels-Alder reaction to do a cycloaddition that we'll see to make other rings. But it's kind of an exotic thing. People don't really think it's a triple bond. It's probably more of a diradical, where the electrons are on each carbon, and they're two sp2 orbitals that are sort of acting like p orbitals. But whatever, it's a benzene. We can just imagine that as like benzene. And so it's acting first as a base, and then what happens after it acts as a base? Is it then acts as a nucleophile. So first we did an elimination. That was to make this. So this is an elimination step. And now we have to do the addition step, and that's just where the nitrogen attacks that. Pushes the electrons. And then, because we have liquid ammonia hanging around, we simply reprotonate our anion, that generating more amide in the process. So it's catalytic for that. So that's the mechanism for that. Mostly I'm teaching you that just so that you know how benzynes are formed for later on in the course. We'll use those benzynes in things. So that's that. Next time we're going to talk about something, we're going to go into chapter 20, and we'll start talking about aldehydes and ketones, which we'll kind of define the rest of the course. We're going to talk about carbonyl compounds and all their reactions. We've been doing aldehydes and ketones for a while. A lot of the most interesting organic chemistry is in aldehydes and ketones, in my opinion. So that's what we'll be starting with, and then we'll be doing 20.1 to 20.4 next time. Any questions before you guys go?